Number 11, a manufacturer claims that the mean life of its lithium batteries is 900 hours, so the claim that the mean is 900. A homeowner selects 25 of these batteries and finds that the mean lifetime to be 880 hours with a standard deviation of 80. Test the manufacturer's claim, use alpha equal 5%. Alright, so here's what we have. We're testing that the mean equals 900 hours, 25 batteries. The sample mean was 880 and the standard deviation is 80. We need to test the claim at alpha equal 5%. So the 5 steps. First step is stating HO and H1. HO is where the equal sign is, so that's going to be the mean equals 900 hours, and that's where the claim. And H1 is the alternative, the competing claim, which is different from 900 hours. Okay, this is a t-test using the calculator, and let me show you how to execute this test. Stat, tests, t-test, not data, it's a summary. Mu0 is the value from the null hypothesis, so that's 900. X bar is 880, S is 80, N is how many? 25, and we need, this is the alternative. The alternative is different from, make sure to select it and press enter and then hit calculate. And the next step is the test statistic t equals what? Negative 1.25. And what's the p-value here? P-value equals 0.2234, which is more than alpha equals 0.05. If the p-value is more than alpha, what's the decision? Fail to reject HO. What's the conclusion? There is not. Every time you use the word fail to reject, you have to begin with there is not enough evidence at the 0.05 level of significance to reject the claim. We cannot reject the claim. Doesn't mean we support it, but we just can't reject it. To reject the manufacturer claim that the mean lifetime of its battery is 900 hours. Number 12, in a recent survey of drinking laws, a random sample of 1,000 women showed that 65% were in favor of increasing the legal drinking age. In a random sample of 1,000 men, 60% favored increasing the legal drinking age. Test the hypothesis that percentage of men and women favoring a higher legal drinking age is the same. Use alpha equals 0.05. Okay, so let's go back. So we need to test the claim that P1, this is the population proportion from the women, equals what? P2, and that would fall under what hypothesis, guys? It's HO. This is the claim. So H1, it's the alternative. The competing claim would be what? P1 different from P2. The test that you need to use here on the calculator, should use the calculator for this test. It's 2 prop z test. I don't expect you to calculate the test statistic or the p-value by hand. So it's a 2 prop z test. And let's begin the test. Enter. Okay, X1. X1 is the number of successes. So the number of women who said that they favor increasing the legal drinking age. Well, we don't know X1, but we know that 60% of the 1,000 favored increasing the legal drinking age. That means X1 is going to be, this is the formula for X1, guys. Let me just so to find X1 is 65% of 1,000, so you just do 0.65 times times 1000, and that will give you 650. N1 is 1000. To find x2 is the same thing. You do 60% of 1000, so which is 0.6 times 1000. Now remember, you need to keep in mind one thing. Let's say you do P1 times N1, it turns out to be a decimal number. You must round it to the nearest whole number, because x1 is a number of successes. It can't be a decimal. So let's say you get 650.3, you must make it 650 or 651. And 2 is 1000. Okay, what's the alternative hypothesis is different from? And then hit calculate, and that's what I need. The next value is z equals, what's z here? 2.31. And what's the p-value? P-value is about 0.0209. And alpha in the exercise, I believe it's 5%. So we got the p-value, which is 0.0209, which is less than 5%. If the p-value is less than 5%, less than alpha, you reject HO. And then you conclude that there is enough evidence at the 0.05 level of significance to reject the claim that the two proportions are equal. So that's number 12. I mistakenly put 11, but that should be number 12. Okay, this is a test for dependent samples in number 13. Every time you see the before and after, you know it's dependent samples. A local company is concerned about the number of days missed by its employees due to illness. A random sample of 10 employees is selected. The number of days absent in 1 year is listed below. An incentive program is offered in an attempt to decrease the number of days absent. The number of days absent in 1 year after the incentive program is listed below. Test the claim that the incentive program cuts down on the number of days missed by employees. Use alpha equals 0.05. Assume that the distribution is normally distributed. So we have 10 employees, A, B, C, D, etc. We have the number of days that they were absent before the incentive, and the same employee, we have their number of days the next year after the incentive. Like the first employee, the year before took 3 days, and the year after, that person took only 1 day off during the incentive program. And the second one, 87772098. So it seems like, after the incentive, the number of days absent were decreasing. So this is what we need to test here. We need to test that the difference between days absent before and days absent after is positive. We want the number before to be larger than the numbers after if the incentive works. So we need the difference to be positive. So here's what we do. We will compute the difference. We do 3 minus 1, 8 minus 7, 7 minus 7, 2 minus 0, 9 minus 8, etc. And we test that this difference is positive. This is how we set it up. So these are the differences, and we need to set it up this way. We need to test that the mean of the difference is greater than 0, and this is my claim. And here the mean, it's just an index here of the difference that should be equal to 0. So this is what you're gonna do, guys. You're gonna input those differences into L1, and you're gonna run a t-test against 0, and let me show you how to do this. Okay, so we're gonna go to onstat, edit. I'm gonna clear L1, and I'm gonna enter those values: 2, 1, 0, 2, 1, 2, 2, save 1, 2, 0. I'm gonna quit. I'm gonna go to tests, stat, and I'm gonna run a t-test. So it's always a t-test for dependent samples after you subtract the two samples. Okay, it's data this time. Mu0, it's always 0 when you do dependent samples. You test against 0. The data, I put it in L1. Leave the frequency alone. 1, don't change it. We need to test a greater than, so it's a greater than. And then hit calculate. And here are the results. So the test statistic T equals 3.16. And p-value is what? P-value is 0.0058. And what is alpha here? Let me check in the question and see what alpha is. Alpha is 0.05. Well, it's obvious that this p-value is less than alpha. So what's your decision? Reject HO. That's step number 4. And if you reject HO and the claim in H1, you support the claim. There is enough evidence at the 0.05 level of significance to conclude that the incentive works in reducing the number of days absent. So that's number 13. Okay, in 14, test the hypothesis that mu1 is greater than mu2. Two samples are randomly selected from normal population. The sample statistics are given below. Use alpha equal 0.005. I think it should be 0.05 here. So N1 is 18, X1 bar is 770, S1 is 40, N2 is 13, X2 bar is 755, and S2 is 25. So let me show you how to perform this test using the calculator. So let's go here. So N1 is 18, that's the data that we have, and we need to test, okay, HO, HA. Since the sign is greater, so it has to go H1 here. It has to go in the alternative. And what is the null hypothesis? It's a mu1 equals a mu2. It's always the equal sign, remember that, and the null. And this is where the claim is. This is a two-sample t-test. Okay. And let me show you how to run this test. We're going to turn the calculator on. Stat, tests, two-sample t-test. Okay. I don't have data, I have summary. Sorry, I have to go back and go to stat, enter. Now, it's asking me for X1 bar, which is 770, S1, which is 40, N1 is 18, X2 bar is 755, S2 is 25, N2 is what, 13. The alternative sign from the alternative hypothesis, it's a greater than. You have to go there and press enter. Pooled. By default, you leave it at no. Pooled means are the population variances equal or not. If it doesn't say anything, so we assume that it's a no. So just leave it at no by default and calculate. And test the statistic T is 1.28 mu2, p-value is what? This is now the third step, the p-value, which is 0.1051, and actually alpha here should have been 0.05. We don't test the alpha at the low value, so 0.05. It doesn't matter, we're going to get the same results. P-value here is more than alpha, so we fail to reject HO. And what's the conclusion? Now you need to interpret your decision in the context of the. So we say there is not enough evidence at the 0.05 level of significance to support the claim that mu1 is bigger than mu2. That concludes this exercise. Number 15, what's HO for testing differences of the means of two independent samples? Well, HO should be that mu1 equals mu2. So let me just write this down. So number 15, HO should be this, mu1 equals mu2. Or you can make it this, if mu1 equals mu2 means mu1 minus mu2 equal to what? To 0. As long as you have the equal sign, you are in the null hypothesis mode. Okay, 16, a random sample of 160 car purchases are selected and categorized by age. The results are listed below. The age distribution of drivers from the given categories is 18%. So if you 18% under the age of 26, 39% from 26 to 45, 31% for 46 to 65, and 12% of the drivers on the street are believed to be all over 65. Test the claim that all ages have purchase rates proportional to their drive-in rates. Use alpha equals 0.05. This is, guys, a goodness of fit test, and we need to perform a chi-square goodness of fit test on this one. You will be given the observed values, you will need to find the expected values, and after that I'm going to show you how to use the calculator to run the goodness of fit test. Okay, so these are the observed values. I'm going to go back to my notes and show you how to work this out. Okay, so 66 are under the age of 26. I didn't write the categories here. 39 from 26 to what, 45, and then 45 to 65, and then over 65. So, and now here we have a 12% in here. So here's how you begin. You begin HO distribution of drivers is as claimed. H1 distribution is not as claimed, or you can say distribution has changed. He wants us to test if the distribution of the, let me just show you. Test the claim that all ages have purchase rate proportional to their drive-in rates as given in this distribution. So the claim is in the null hypothesis in this case. So let's go back to our note. That's where the claim is. Okay. Let me show you how to find the expected value, and then I'll show you how to use the calculator. We have if you add all the observed values, actually he gave us the total. The total is 160. 66 plus 39 plus 25 plus 30 will give you 160. So in order to find the expected value, you need to find the percentage of the total for each one. So 18% of 160. Then the next category, you need to find 39% of 160. Then the next one, you have to find 31% of 160. And finally, 12% of 160. So here is what we do. You go to stat. So turn the calculator on first. Stat. Edit. In L1, okay, I'll go up to L1 and clear it. Don't hit delete. The L1 will disappear if you hit delete. So I have the value 66. I have 39. I have 25. I have 30. Enter. Now I'm gonna go to L2 and enter the expected value. So I'm gonna clear this one first. Okay, for the first one it's 18% of 160. You can simply put 0.18 times 160. Enter. The next one, 0.39 times 160. Enter. The next one, 0.31 times 160. Enter. And then one more, 12%, 0.122 times 160. There you go. And now I'm gonna quit. Then I'm gonna run the test. You go to stat, tests, scroll up. It's D, chi-square goodness of fit test. So let me just write this here. Goodness of fit test. Okay, it says the observed in L1, that is correct. The expected in L2. Now, degrees of freedom, if number of categories -1, since I have 4 categories, -1 will be 3, so you need to change this one and then hit calculate, and here's chi-square, which is 75.10. P-value, it says 3.4474. Don't forget there is E minus 16. That means this, guys, 45, let me round it, times 10 to the negative 16, which is almost 0. Once you see the E to the negative number, you know your p-value is very small. It's almost 0. And this is less than what? Alpha. Regardless what alpha is, so we reject what? HO. So what's our conclusion? We interpret our decision in the context of the claim. We say there is enough evidence at the 0.05 level of significance. Okay. Level of significance. Okay, there's enough evidence to reject the claim that distribution of purchase rate by age is as claimed above. That means it has changed. 17. This is a test for independence. A sports statistician is interested in determining if there is a relationship between the number of home team and visiting team losses and different sports. A random sample of 526 games is selected and the results are given below. Test the claim that the number of home team and visiting team losses is independent of the sport. Okay, so let's do this. Okay, he wants us to test that the number of home team or visiting team losses is independent of the sport. So that should be HO, because HO, you make this statement in HO always. The variables are independent. In H1, you make the statement the variables are dependent. In our case, in this problem, the variables are the number of home team, visiting team losses, and the sport. So one variable is the number of home team losses, and the second variable is the type of sport. So our claim actually happened to be this time in what? In HO. Because he says test the claim that the variables are independent. Okay, I got the table, the contingency table, so I'm going to show you how to run the test on the calculator. First of all, we're going to enter, those values, the contingency table, in what we call a matrix. So I'm going to go to second in matrix, which is X inverse. I have to go to edit. How many rows do I have here? So I'm going to go to first one, press enter. Now I have 2 rows and 4 columns. Well, actually this calculator actually this is exactly the same data, so I think I did this exercise somewhere else. So you just typed in 2 times by 4 and then hit enter, and then you enter the data like 39, 156, 25, etc., 83, and then you enter the remaining values, and that's it, and then you quit. Then we will go to stat, tests, scroll up, and the test is the chi-square test. This is the test of independence. So remember that this is the test for independence. So I'm going to scroll up, enter. Very easy test on the calculator. It's asking me the observed values are A. Expected values, the calculator is asking if it can put the expected values in B. You didn't find them, but on the calculator you don't have to find them. The calculator will do the job, and then just hit calculate. As simple as that. Here is the test statistic. Chi-square is what? 3.888. P-value is what? 0.2738, which is large, which is more than alpha. 0.01. So what's your decision? Fail to what? Reject HO. If we fail to reject HO, what's the conclusion? There is not enough evidence at the 0.01 level of significance to reject the claim. We cannot reject the claim. Doesn't mean that the claim is true, but we just can't reject it. Okay, number 18, the grade point average of students participating in sports at the local college are to be compared. The data are listed below. Test the hypothesis that there is no difference in the mean grade point average of the three groups using alpha equal 0.05. So here we're comparing more than 2 means, 3 means. When we do that, this is what we call one-way analysis of variance, which is called ANOVA test. So the first thing that you guys have to do is to enter the data into lists L1, L2, L3. And let me show you how we go about doing this. I already have the lists. As you can see, I input them to save time. And what is the question again? He says test the hypothesis that there is no difference. So this is how you state the null and the alternative. 18. You have 3 means here. Your HO should be this statement always. 4 different sets, then you add equals mu4. And your H1 should be exactly what I'm writing here, regardless of what the problem is. At least one of the means is different from the others. Next step, you're gonna use calculator for this. I'm gonna quit. I'm gonna go to stat, tests. I'm gonna scroll up to ANOVA, and then you're gonna enter L1, L2, L3. So you just go to second, 1, comma, second, 2, comma, second, 3, close, and here you go. So we did ANOVA, L1, L2, L3. The test statistic for the test one-way analysis of variance is called F, so you write down F equals 1.56. The p-value, guys, as you can see, it's what? 0.2498, which is more than alpha. So what's your decision? Fail to reject. HO. He asked us to test that there is no difference in the means, so the claim was actually in HO. So we say there is not enough evidence at, what was alpha, 0.05? At the 0.05 level of significance to reject the claim. Cannot reject the claim. So that's exercise number 18. Okay, 19. This is section 4.1. The data below are the final exam scores of 10 randomly selected calculus students and the number of hours they slept the night before the exam. Calculate the linear correlation coefficient. The linear correlation coefficient will give us an idea if there is a linear relationship between the number of hours and the scores on the exam. So linear correlation coefficient is called R. If R is very close to 1, then we can make a conclusion that there could be very strong positive linear relationship between the variables. If R is very close to -1, we can make a conclusion that there is a strong negative linear relationship between the variables. But if R is close to 0, the linear relationship is very weak. So in order to find R, guys, first of all, you would have to input this data here that I'm selecting for the hours in L1 or whatever list you choose, and then you have to put the scores in another list. Let me show you how to go about doing this. So what I did here, stat edit, I think I put him in L4 and L5. So I have my list in L4 and L5. Now, in order to make sure that R is gonna show up on the screen, you would have to do this if you haven't done it yet. So you go to second, catalog, and then you scroll down until you see diagnostic on. Oops. So diagnostic on, let's leave it there. Okay. And there you go, diagnostic. Press enter twice. So let's just move it up so I can reach it. Now whatever I do, it's gonna show the value of R. So let me show you how to do that. That is how we do it. We go to stat, calc, linear regression, AX plus B. It's asking me where is my list. I think I put him in L4 and L5, so I do second and 4. If you put him in L1, L2, just leave this. Second and 5. I suggest, guys, that every single exercise that I'm doing, you just do it. So if you see it on the test or you see something similar to it, you should be able to do it. I wouldn't do anything here. I wouldn't do anything here. There, I just go to what? Calculate. And you can see the value of R here. So R is 0.8465. If interpret it, you can say that there seems to be a positive. I don't know, it's very strong because it's not very close to 1, but it is close to 1. There seems to be a positive linear relationship between the number of hours slept and the score on the calculus exam. So your conclusion, R is 0.847. There seems to be a positive linear relationship between the number of hours slept and the score on the test. Number 20, the data below are the number of absences and the final grades of 9 randomly selected students from literature class. Find the equation of the regression line for the given data. What would be the predicted final grade if a student was absent 14 times? Round the regression line value to the nearest hundredth, so 2 decimal places. Round the predicted grade to the nearest whole number. So again, guys, first of all, you would have to enter the number of absences in a list, and then the final grade and another list. I've done that already, so let me just show you what we're gonna do here. So I put my data into L1 and L2, and I'm gonna run now, go to stat, calc. Again, it's number 4, that's the equation of the line, linear regression. Okay, I have my data in L1 and L2, so second and then number 1, I'm going to go back to L1 and L2. You don't do anything here, press enter, and here's my equation. Let's just move this a little bit and show you the equation, number 20. Since this equation was generated from a sample, we call it y hat. He said he wants 2 decimal places, and the equation is ax plus b. So what's the value of a? Negative 2.75. X, just follow the calculator screen. B is 96.14. Now he asked us a question. What would be the grade if a student was absent 14 times? So that means in this case we're gonna make x equals 14. So y hat will be negative 2.75 times 14 plus 96.14, and I'll let you do the math here. So that's how we do number 20. Okay, for the exercise 21, I'll show you. The table below shows the ages and weights in pounds of 9 randomly selected tennis coaches, age and weight. So first of all, guys, you have to put the age in L1, the weight in L2. He wants a linear correlation coefficient and state whether there is a linear relationship between the 2 variables. So you put age in L1, weight in L2, and then you go to stat, calc, and then number 4, linear regression ax plus b. You press enter, you select L1 and L2, it's gonna give you the value of R. I'm gonna save time here and end this video. So R, I think it's gonna be 0.96. Now how can you check if a linear relationship exists? In table 2, you would find what we call a critical value. How do you find the critical value? You just go to the sample size, and the sample size in this problem we have 9 coaches. Next to n9 equals 9, you're gonna find a critical value on the same row is 0.666. You take the absolute value of R. If the absolute value of R is bigger than the critical value, then you can conclude then there is a linear relationship between the variables. Otherwise, if the absolute value of R is less than the critical value, then you say that there is not a linear relationship. In our case, absolute value of R value of R is 0.96, which is bigger than the critical value 0.66, then you can conclude that linear relationship exists. Very simple tests. If I ask you a question like that, I will provide you with the table, so you'll have table 2. That's what you use it for. Last question, given the equation of regression line is y hat is for x minus 10, what's the best predicted value for y given that x equals 8? So all you do, guys, is just plug in x equals 8. So if I am to do this, and when x is 8, y hat will be what? 4 times 8 minus 10.